Welcome. In this explainer, we're diving into some fantastic research material for educators from Dr. Sudheendra S G. We're going to pull back the curtain and demystify the incredible architecture that lets billions of computers, phones, and all our devices talk to each other every single second of the day. You know, it's kind of wild to think about. Just 150 years ago, sending a message across the country took weeks. Weeks! Today, an email can circle the entire globe in, well, the blink of an eye. This incredible leap didn't just happen. So how on earth did we build the digital roads to make it all possible? We're going to find out. Let's start small, in a single room, and then zoom all the way out to the entire planet. Okay, so it all starts right here, on the smallest scale, the local area network, or what we all call a LAN. For your students, you can have them picture a few computers in a classroom, all hooked up to the very same cable. Super simple, right? But it brings up a really interesting question. If everyone's talking on the same line, how does a message actually find the right computer? Well, the solution is something called a MAC address. Every single device, your laptop, your phone, everything, has one, and it is totally unique in the whole world. The best way to think of it is like a device's own special fingerprint burned right into its hardware. So when one computer sends a message, it's like it puts the recipient's fingerprint on the envelope. Every device on the line hears that message, but only the one with the matching MAC address actually opens it up and reads it. Pretty clever. But see, this system, as clever as it is, creates a brand new problem. If anyone can talk at any time, what happens when two devices try to send a message at the exact same microsecond? It's kind of like an old party line phone call where two people start talking at once. What you get is this, a collision. The two messages literally crash into each other on the wire. Their data gets all scrambled up, and everything becomes completely useless. It's the network version of two people shouting over each other. Nobody can understand a thing. The brilliant solution is a protocol with a pretty long name, CSMA/CD. But it's basically just a set of digital manners. The rules are simple. Listen before you talk. If the line's clear, go ahead and send your message. But if you accidentally interrupt someone and cause a collision, you both stop talking immediately, wait a random amount of time, and then you try again. And that random part, that is the absolute key. It stops the same two devices from crashing into each other over and over and over again. Now, this whole system works pretty well when you've got just a handful of computers. But what happens when you add dozens or 100? Well, the line gets super busy, collisions start happening all the time, and the entire network just grinds to a halt. That whole shared cable becomes one giant collision domain. So how do we fix this digital traffic jam? We bring in a traffic cop, and that's the network switch. A switch is way, way smarter than just a simple cable. It actually learns which computer lives on each of its ports. So when a message comes in, instead of shouting it out to everyone, it creates a private, temporary connection directly to the computer it's meant for. This is a great way to help your students visualize network segmentation. It's like the switch gives every single conversation its own private lane on the highway. Okay, so we figured out how to build a fast, efficient local network. We solved that collision problem. But what about the really, really big picture? How do we connect the LAN in your school to a server or maybe another student on the other side of the planet? Well, the early engineers had three main ideas on the table. The first was circuit switching. Think of an old telephone call where you get a whole private line reserved just for you. The second was message switching, which is kind of like the postal service, where your whole letter gets sent from one post office to the next. But the modern internet, it's built entirely on the third idea. And that idea is packet switching. This is the crucial concept. Instead of sending one giant file, packet switching chops up every single email, every video, every web page into thousands of tiny little pieces called packets. Each one of those packets is sent out into the world on its own, and then they're all perfectly put back together at the destination. Now, for this whole global system to work, we need a totally different kind of address. Not that local MAC address, but a global IP address. And this works just like the mailing address for your house. It tells all the routers in the world exactly where to send these little packets. Now, what's really cool is how these two addresses work together. Think of it this way. The IP address is like the street address of a big apartment building. It gets the package to the right building anywhere in the world. The MAC address is like the person's name on the mailbox. It gets the package to the right person inside that building. You absolutely need both to get something from anywhere on Earth right to your hands.
So this packet system is amazingly flexible and tough, but it creates a new kind of danger. With millions of routers all making their own decisions about where to send things, what's to stop a packet from getting caught in an endless loop, just bouncing between two routers forever and clogging up the entire internet?
The solution is so simple, it's genius. It's a little self-destruct timer inside every packet called Time to Live, or TTL. So each packet is born with a number, let's say 64. And every time it passes through a router, a hop, that number ticks down by 1. If it ever hits 0, the router just destroys it. Poof, gone. And that is how the internet automatically cleans up after itself, protecting it from getting bogged down with lost data.
So when you put it all together, it becomes really clear why packet switching was the big winner. 1, it's incredibly efficient because it uses every tiny bit of empty space on the network cables. 2, it's robust. If one path breaks, the packets just find another way around, no big deal. And maybe most importantly, it's decentralized. There's no single central master control switch that can bring the whole thing crashing down. You see, the original internet, ARPANET, was actually designed for the military with this exact idea in mind. It had to be able to survive potential failures. And today, that very same decentralized principle allows a global network of billions of devices to operate reliably 24/7 without any single person or any one company being in charge. And that leaves us with a final, really powerful thought. This design, it's not just about technology, it's a huge idea. You can cut a single cable, but you can't cut a connection that's woven together from millions of different threads. It really shows us that systems that don't have a single point of failure, whether we're talking about technology or society or even how we think, those are often the ones that last the longest and grow the strongest.